In the last video, we talked about graphing functions. In this section, we're going to talk about different things you can say about a graph based on the function. And then for functions that don't fit into a nice category from a parent graph, what can we say about their graphs if we can't graph from a parent function? And finally, we're going to talk about functions that are defined by multiple rules. We're going to call these piecewise-defined functions. So the first thing we could talk about in terms of a graph is any symmetry the graph may have. So a graph is symmetric with respect to an axis if it lays on top of itself when folded across that axis. So we have graphs that may be symmetric with respect to the x-axis or respect to the y-axis. We can also have graphs that are symmetric with respect to the origin. A graph is symmetric with respect to the origin if it lays on top of itself when folded across both axes. So we have to fold it across the x-axis and the y-axis, and it has to coincide with itself. Another way of describing origin symmetry is if the graph lays on top of itself when it's rotated 180 degrees. Let's look at some examples of symmetry as determined by graphs. So a graph that has y-axis symmetry might look like this. This should look familiar. This is the absolute value parent function. So if we were to fold one half of the graph across the y-axis, it would coincide with the other half of the graph. That's what we mean by y-axis symmetry. An example of a graph that has x-axis symmetry might look like this. So this particular graph is actually the graph of the equation x equals y squared. So we've seen y equals x squared, or otherwise f of x equals x squared. This would be x equals y squared, where the x and y have switched places. So if we were to take one half of this graph, either the half that's above or below the x-axis, and then flip it across the x-axis, it would coincide with itself. So this is x-axis symmetry. An example of origin symmetry comes from the cube parent function. So we can look at this two ways. Either we take one half of the graph, so one branch of the graph, and then flip it across the x and y axis, or you can think of rotating this graph 180 degrees. In either case, the graph will lie on top of itself, which is what we mean by origin symmetry. So one thing we need to consider is, do these graphs represent functions? Remember, the way to check whether or not a graph represents function is using the vertical line test. So if a vertical line passes through the graph twice anywhere on the graph, then it is not a function. For our first graph, we can draw a vertical line anywhere we want on that graph, and it's only going to cross the graph one time. So the first graph represents a function. For the second graph, we can draw a bunch of different vertical lines that will cross the graph twice, so this is not a function. In general, x-axis symmetry does not correspond to a function. For the last graph, we can draw a vertical line anywhere we want, and it will only cross the graph one time, so it is also a function. So to summarize, functions can have y-axis symmetry and they can have origin symmetry, but they cannot have x-axis symmetry. But what if we don't have a graph? What if we just have an equation and we want to determine, without graphing the equation, whether or not the graph will have any symmetry? Well, we have a few tests for symmetry that we can apply to any equation with the variables x and y. So given an equation with the variables x and y, the graph is symmetric with respect to the y-axis if substituting negative x in place of x results in an equivalent equation. So if we plug in a negative x and can fully simplify the equation and it returns to its original form, then that means that our graph, were we to graph it, is going to be symmetric across the y-axis. The graph is symmetric with respect to the x-axis if substituting a negative y in place of y results in an equivalent equation. And finally, the graph is symmetric with respect to the origin if substituting both variables as negatives results in an equivalent equation. So the idea is we substitute in negatives. Notice for y-axis and x-axis we're substituting for the opposite variable. In any case, we substitute the negative version of the variable, and if we can use basic algebra to simplify and eliminate the negatives and return it to the original form of the equation, then that means we officially have that particular type of symmetry. So one hint to keep in mind is that if an equation tests positive for two symmetries, then all apply. So it's not possible to have two types of symmetries and then the other not apply. We either have one type of symmetry that works, no type of symmetries that work, or all three symmetries will have to apply. So let's do an example where we test an equation for the three types of symmetry. Our equation is y equals x squared minus 4, and we want to test for y-axis, x-axis, and origin symmetry. So the goal for each of these is once we plug in a negative, we want to try to get rid of that negative or the negatives in the problem. Another way of saying that is we want to use whatever algebraic skills we have to change the equation with the substitution made so that it mirrors the original equation that we're testing. So for y-axis symmetry, we're plugging in a negative x in place of x. Now we want to see if we can simplify this equation at all. We know that when we square anything negative, it makes the negative positive. So simplifying this, we now have y equals x squared minus 4. Well, this equation is exactly the same as the one we started with. And by definition, that's what we mean by y-axis symmetry. When we plug in a negative x, the negative goes away. So in this case, we have y-axis symmetry. To check x-axis symmetry, we're plugging in a negative y in place of the y. The parentheses here don't really change anything, so we can drop those off and just write a negative y without them. Again, the goal is to get rid of that negative and turn it back into a regular y. The only way to do that here is to divide by a negative 1. But if we divide by a negative 1 on the left, we have to do it to the right side of the equation as well. If we do that to the right side, we're going to flip all of our signs, and we're not going to have the same equation we started with. There's no way we can get rid of the negative in this problem without just moving it around from side to side. That means we do not have x-axis symmetry. The substitution can't be eliminated. There's no way we can get back to the original equation. So based on the hint we had from the previous slide, we know that in theory, origin symmetry should not work as well. We either have one type of symmetry, no type of symmetry, or all three must apply. But let's prove that origin is not going to work in this case. So for origin symmetry, we plug in a negative x and a negative y, and we see if we can simplify from there. So again, with the parentheses around the negative y, nothing really changes, so we can remove those parentheses. And then squaring the negative x makes the negative go away. So we're left with negative y is equal to x squared minus 4. Now we return to the same spot we were in with the x-axis symmetry test. We have that negative on the left-hand side of the equation. The only way to move it is to divide by a negative 1, but once we do that, we just move it to the right-hand side and nothing really changes. So we're in the same situation, we can't get rid of this negative. That means we do not have origin symmetry either. So for this particular equation, which is actually a shifted parabola, it's a transformed version of the quadratic parent function, the only type of symmetry we have is going to be y-axis symmetry. Let's try another one. So our next equation is the absolute value of y is equal to x plus 1, and we want to test for our three types of symmetry. So for y-axis symmetry, we plug in a negative x in place of our x. The parentheses don't make a difference here, so we can drop those off. Now our goal is to get rid of the negative in front of the x. We could divide it out, we could move the x over. In either case, we're going to end up with an equation that doesn't match the original one. We can't get rid of this negative. There's nothing we can do without fundamentally changing the equation, so we do not have y-axis symmetry. For x-axis symmetry, we plug in a negative y in place of y. Notice in this case the negative is now inside of an absolute value. Absolute value changes negative numbers into positive numbers, so the absolute value is actually going to eliminate the negative inside of the bars. In this case, once the negative is eliminated, we have the same equation we started with. So we do have x-axis symmetry because plugging in a negative y doesn't change the equation. Let's check origin symmetry. We know in theory it shouldn't work because we have one type of symmetry working and the other one doesn't, but let's prove that origin symmetry doesn't apply. So now we're plugging in negative x and negative y. The negative in the absolute value bars again is going to go away, but we're going to be left with that negative in front of the x. And as we decided before, there's nothing we can do to fundamentally get rid of that negative without changing the equation. So in this case, origin symmetry does not apply. So for this equation, we have x-axis symmetry and no other type of symmetry. If we were to graph this equation, it would look like the absolute value graph, but it'll be oriented along the x-axis. Let's try one final example. So our final equation is x squared plus y squared is equal to 9, and we want to test for all three types of symmetry. So for y-axis symmetry, we're plugging in a negative x in place of x. Again, we're squaring, and as we've already decided, squaring eliminates a negative, so we're left with x squared plus y squared is equal to 9. In this case, this particular equation matches the original, so we have y-axis symmetry. Now let's check x-axis symmetry. We plug in a negative y in place of the y. The y is also squared, which in this case means that the negative in front is going to be eliminated. Yet again, we run into the same situation. We now have an equation that matches the original, which means we have x-axis symmetry. So in theory, we know origin symmetry should work. We either have one type of symmetry, no symmetries at all, or we have all three. But let's prove that origin symmetry is going to apply. So now we're plugging in a negative x and a negative y, and we want to eliminate both of those negatives. Both the x and the y are being squared, which means both negatives will be eliminated. We'll have the original equation we started with, so we have origin symmetry as well. So this is one example of an equation that has all three types of symmetry. The reason this equation has all three types of symmetry can be determined from the graph. If we were to graph this equation, this is actually the equation of a circle centered at the origin. So for a graph like this, we could fold it across the y-axis, we could fold it across the x-axis, and we could fold it twice, or we could rotate it 180 degrees, and we'll have the same graph we started with. So let's sum up what we know so far about symmetry. Given an equation with x and y, the equation's graph can have one type of symmetry, three types of symmetry, or no symmetry at all. There's no way for an equation to have two types of symmetry and not a third. The reason for this is that if the equation's graph is symmetric with respect to both the x and y axis, then it's automatically symmetric with respect to the origin by definition. So it's pretty much an all or nothing situation. Now let's put this in the context of functions. We know that a function can't be symmetric with respect to the x-axis. Any graph that has an x-axis symmetry will fail the vertical line test, so it won't actually be a function. So this leaves only two possible symmetries, y-axis symmetry and origin symmetry. But we just decided that we can't have two without having all three. What this means is that for any function specifically, the function's graph will either be symmetric with respect to the x-axis, symmetric with respect to the origin, or not symmetric at all. These three possibilities give us a way to classify functions in terms of whatever symmetry they have. We classify them as even, odd, or neither. We also adapt the symmetry tests to make them work for function notation. Since a function can only fit under one of the three classifications, we can reduce everything down to a single test. We perform one test, and based on the outcome, we decide which case our function falls under. Keep in mind, this only applies when we have a function. For any generic equation, we still have to use the three symmetry tests to get our key information. So here's our test. Given a function f of x, we're going to replace x with negative x. So our test essentially looks like the test for y-axis symmetry. So we perform this one test, and based on our outcome, that tells us whether we have an even function, an odd function, or some function that's neither even nor odd. So the first possibility, a function is even if f of negative x equals f of x. In this case, the graph of the function has y-axis symmetry. So essentially, if we end up with the exact same result as the y-axis symmetry test, we plug in a negative x and the negative goes away, then our function is considered to be even. Practically speaking, if we're plugging in the negative x and the negative goes away, this means that all signs in the function stay the same. So once we simplify everything down, everything we obtained from plugging in a negative x, if all the original signs in the function are still the same, then that means our function is even and it's going to have y-axis symmetry if we graph it. Another possibility is an odd function. So if we plug in a negative x, and that's the same thing as negative f of x, then that is an odd function. In this case, the graph has origin symmetry. So what does this look like? Well, if all the signs flip, that's another way of saying we're taking the negative of the original function. So if we plug in negative x, and as opposed to all the negatives going away, all the signs in the equation flip, that means we have an odd function that has origin symmetry. And it's also possible that we could have a situation where the test is completely failed. We don't fall under either of these special cases, so our function is neither even nor odd. This happens if some of the signs stay the same, but some of the signs flip. So if we're somewhere in the middle between these two cases, then our function's neither even nor odd, and we don't have any special symmetry. So one thing to keep in mind is that a function cannot be both even and odd. So we just decided we can't have both y-axis and origin symmetry with a function, because then we'd also have to have x-axis symmetry. So when we perform this test, we're going to fall under one of the three cases, never any combination. So let's start by determining even and oddness from a graph. So we're going to use the graph to determine whether the related function is even, odd, or neither even nor odd. So let's look at our first graph. Our first graph definitely has y-axis symmetry. There's a mirror image across the y-axis. Y-axis symmetry means the function is even. So in this case, whatever function generated this graph is an even function. This next one doesn't have any type of symmetry. Notice it's not even centered at the origin. It's pretty much a giveaway. If your function's graph is not centered at the origin, then it's not going to have any symmetry. So in this case, because we don't have y-axis symmetry or origin symmetry, this function is neither even nor odd. Keep in mind it is still a function, it's just not specially classified as an even function or an odd function. And finally, this particular function is centered at the origin. There's sort of a diagonal symmetry going on. So if you were to take one half of the graph and flip it twice, or if you were to rotate the graph 180 degrees, it would lay on top of itself. So in this case, it's an odd function. So one thing I want you to keep in mind is that even and odd are not the norm. They're honestly special cases. So if you were to just write a generic function without doing any type of testing or really thinking too much about it, chances are what you would write would be neither even nor odd. Even functions and odd functions are special cases. They only occur in a situation where our graph is centered at the origin and is a very well-behaved graph. Now let's use our algebraic test to determine even and oddness for a function and function notation. So here's our first function. F of x is equal to negative 2x to the fourth plus 5 times the absolute value of x. So our function notation test involves plugging in a negative x in place of x. So everywhere there's an x in this function, we're going to put a negative x in place of it. Now our goal is to simplify this equation as much as we can. So essentially we're taking the right-hand side and we're using all the basic algebraic rules we know to simplify what we have. So what we need to simplify is anything where we plugged in a negative x. So for the first term where we plug in a negative x and we raise it to the fourth power, we need to know what exponents do to negatives. Anytime we have an even exponent, the exponent cancels out the negative. So squaring something or raising something to the fourth or sixth or eighth power, etc., forever and ever, anytime we use an even exponent, it's going to make a negative go away. So in this case, taking that negative x and raising it to the fourth power, the negative cancels out. With the absolute value bars, we decided before that absolute value takes negative things and makes them positive. So the absolute value bars are also going to cancel out the negative. So in this case, once we simplify it down, we're left with negative 2x to the fourth power plus 5 times the absolute value of x. This result is the same as the original function. In other words, all the signs from the original function are the same. We have a negative out front, we have a positive after that. None of the signs have flipped. So that means this is an even function because all the signs in our resulting function are the same as the signs in the original function. Let's try another one. So we want to determine whether this function is even, odd, or neither, and our function is f of x is equal to 4x cubed minus x. So we perform the same test. We plug in a negative x in place of x, and then we're going to simplify. So now we have an odd exponent. Anytime we have an odd exponent, if we're applying an odd exponent to a negative, it stays negative. So in this case, taking a negative x and cubing it, the negative is not going to be canceled. It's not going to go away. It's going to be maintained as part of the function. So if we're keeping the negative, we can actually pull the negative out to the front of the term. So negative x cubed stays negative. We just pull the negative out in front of the 4. Well, what about the second term? We're subtracting a negative x. There's no exponent, but subtraction of a negative we typically rewrite as addition. So our fully simplified function now is negative 4x cubed plus x. So the signs are definitely not the same as the original function, but notice that both signs are flipped. So in the original function, it was a positive followed by a negative. Well, now we have a negative followed by a positive. Both of the signs have flipped. This means that this is an odd function. So if we were to graph this function, this is going to have origin-based symmetry. Let's try one more. So now our function is f of x is equal to 2x squared plus x. Same test, so f of negative x, plugging in a negative x in place of all the original x's. We have a square, and then we have something that has no exponent. So there's actually an understood exponent of 1 on the second term. For the first term, where we're squaring the negative x, squaring makes the negative go away. So that negative x squared just becomes an x squared. For the second term, we're adding a negative x. Well, the cleaner way to write that is subtraction of x. So if we simplify this down, we have 2x squared minus x. So now we compare it to the original function. Notice the first sign has stayed the same, and then the second sign has switched. So this case, we're neither even nor odd. We either have to have all of the same signs or all of the opposite signs. If we're somewhere in the middle where one sign is flipped and another one hasn't, or maybe some combination with more terms, then our function is neither even nor odd. So evenness and oddness is just a helpful way to classify functions that may be more complicated to graph. You may have noticed with all these functions we have, they combine parent functions in a sense. So there's no way to strip things off and condense them down to one parent function that would be easy to graph. So as of right now, these three functions we just looked at, we don't have a really good way to graph them. However, just by doing this test, we can automatically say some things about what the graph would look like without actually having to take the time to graph them. So symmetry is just one aspect of graphing that gives us a little more information about what the graph looks like, what the general structure is, and then also what the function looks like based upon what the graph looks like. Now let's talk about a special kind of function called a piecewise-defined function. So this is not a new type of function in the sense that it's a parent function. It's just a different way of defining a function based on what the rules are for the function. So sometimes, depending on what situation we're in, we may not be able to determine an output from the same rule for every different type of input. So if we have to apply different rules for different inputs, we create what we call a piecewise-defined function. So some functions use different rules for different parts of their domains. Remember, the domain is just the set of all things we can plug into the function. So now we're talking about a situation where for different inputs we have to use different rules. We call this a piecewise defined function. In other words, the function is defined in pieces. So one example of a real-world situation where we use a piecewise defined function is actually the federal tax bracket system. So if you think of your input as your income level for the year, depending on what your income level is, the IRS uses a different rule to calculate your tax liability. So for higher incomes, they use a specific rule to calculate tax liability. For lower incomes, they use a specific rule for those. So depending on what range of values you fall under for your income for the year, the IRS will use a different rule to determine what your tax liability is going to be for your specific income. So this is an example of a piecewise defined function because there's different rules for different ranges of incomes. So these are kind of Franken graphs, for lack of a better way to put it. The graphs often have holes or breaks. So if you just look up a random graph of a function and there's just a ton of mess going on everywhere, there's holes, there's breaks, there's just tons and tons of pieces, chances are what you found is a piecewise defined function. So odds are each of the individual pieces in the graph corresponds to a different function rule. So if we want to evaluate with specific inputs, in other words, determine what the output is going to be for whatever input we're given, we first have to determine which rule applies to the input. An individual rule will apply to specific inputs. One thing to keep in mind is that there's never going to be any ambiguity about which rule applies. For every individual input, only one rule will apply. There's never a situation where we would have more than one rule that applies to the same input. If that were the case, then we have something that's not a function. Remember, we defined a function as something for which every input has exactly one output. So if there were a possibility that we could plug something in and get two different outputs from it, that by definition is not a function. So for every specific input, we determine which rule applies based on criteria that were given for the function. So let's take a look at a piecewise defined function. So we're going to define our function and we want to evaluate for some specific values of x, some specific inputs. So this is what a piecewise defined function looks like. Notice we still have the notation f of x on the left-hand side, but the right-hand side has definitely changed. So what we call the right-hand side is a stack. It's a stack of rules and a stack of criteria. So we have three separate rules that apply to this function, and notice next to each of the three rules there's a specific limitation on x. So that limitation on x tells you which values that rule applies to. So for the top one, for the top rule, the first rule, it specifically says for x less than -1. So that means if we're plugging in an input that's strictly less than -1, then we're going to use the first rule. Those are the only values of x for which the first rule is going to apply. For other values, we're going to use different rules. So our second rule says the output is always -3, regardless of what the input is. The output is always -3. This specifically applies when our input, when our x value, is between -1 and 2, including -1 but not including 2. So any x value that falls in that range, we're going to use the second rule for determining an output. And finally, our third rule applies for any x value greater than or equal to 2. So if we plug in something greater than or equal to 2, we disregard the first and second rule, and we use the third rule. So let's try a couple examples. So f of -3. So first thing I need to do is I need to determine, based on my input, which rule am I going to use. Keep in mind, this particular input is only going to fit into one of the three limitation criteria. So -3 can only fit in one of those limitations on x. So in this case, -3 is less than -1, so that means we're going to apply the first rule because -3 fits in the first x limitation. So we use the first rule, -3 minus 1, simplify it down, and we get an output of 2. So if we plug in -3 to this function, the output is uniquely the number 2. Let's try another one. So f of -1. -1 is kind of a special number. It's a boundary number. So notice -1 is actually included in two different limitation criteria. It's included in the first and second. So we have to decide which one does -1 actually fit under. Well, for the first one, for the first rule, it says this applies for x strictly less than -1. And for the second rule, it says this applies for -1 less than or equal to x less than 2. So in this case, we're going to apply the second rule because the equal to -1 part is included as part of the second set of criteria. So the second rule says regardless of what we plug in, the output is always identically -3. So our output for -1 is -3. What about f of 2? 2 is another one of those boundary points. So 2 is included in criterion 1 and criteria 2 and criteria 3. So criteria 2 says x greater than or equal to -1 and less than 2. Criteria 3 says x strictly greater than or equal to 2. So because we have the equal to as part of the third limitation, that means we're going to use the third rule. So this rule says take the square root after subtracting 2. So square root of 2 minus 2, in this case square root of 0, is equal to 0. So our output for an input of 2 is going to be 0. One more, f of 6. So 6 is definitely greater than or equal to 2, so we're going to use the third rule. So it's the square root of 6 minus 2, which is the square root of 4, which is 2. So in each of these cases, there's more to it than just taking the rule, plugging in a number, and solving using algebra. We have to make sure we know which rule applies. Determining which rule applies is always the first step, and for any input, only one rule is going to apply, and it's going to be based upon that criteria for the domain that we have on the right-hand side. Now let's try graphing one of these. So we have a piecewise defined function, two particular rules, two sections of the domain. So what we're going to do to graph this is we're going to break it down into two pieces. We're going to graph each of these rules individually, and then we're going to combine them together into one graph. So the first piece is f of x is equal to -3x, and this specifically applies for x less than 1. So it applies for the domain from -infinity to 1, not including 1. So we want to forget about the second rule for the moment, just focus on this first rule, and we want to graph that individually as a graph. So this is a linear function. Notice there's no plus a number on the end, so it's in slope-intercept form, but we don't have the y-intercept given. Well, if the y-intercept isn't given, that means it's an understood zero. So this is a linear equation. This is a diagonal line that goes through the origin, through y equals 0, with a slope of -3. So if we graph this, it goes through the origin with a slope of -3, and it stops when we get to x equals 1. Well, how do we know this? Well, specifically, we're told this function rule only applies when x is less than 1. So once we get to the point on the x-axis where x equals 1, we cut off the graph. So we keep everything less than that. We keep all the x values less than 1. Any point that would be on that line where x is greater than 1, we're going to drop off that portion of the graph. So we only keep the portion of the diagonal line for which we have -infinity to 1 on the x-axis. Now we're going to look at the second piece. So for piece 2, the rule is f of x is equal to -3, specifically for when x is greater than or equal to 1. So in other words, for the rest of the x-axis, for the rest of the domain, for any other value besides the ones we've already covered in piece 1. So f of x is equal to -3. Well, think of that as y equals -3. That's going to be a horizontal line that goes through -3. But again, keep in mind, we're only keeping a small portion of that horizontal line. We're only keeping the portion for which x is greater than or equal to 1. So if we were to project it onto the x-axis, we only want the portion that's to the right of x equals 1. So we're only keeping that small portion. Anything to the left is not covered under this particular rule. It's covered under the previous one. So we have two small pieces that generate different graphs. To generate the graph for the whole function, for the piecewise-defined function, we actually take these two and we stick them together. So combined, these two graphs generate the graph for the whole function. Each one is an individual piece given by an individual graph for one of the individual rules. The biggest thing to keep in mind here is what's going on with the domain. So make sure you know where each of these graphs cuts off. The border is at x equals 1. So that point, that juncture where they meet at that one point, that's at x equals 1. To the left, one rule applies, so one portion of the graph. To the right, another rule applies, so another portion of the graph. Let's try another one. So now our function is defined by two rules for different portions of a different domain. So we have one rule. First rule is f of x is equal to x plus 3, and this only applies for x values strictly less than -1. So everything from -infinity to -1, we apply this rule. So this is another linear function. This is also in slope-intercept form. So we have a y-intercept of 3, we have a slope of 1, and we only want to keep the portion of this diagonal line where the x values are less than or equal to -1. So if we generate this graph, this is what we're looking at. Notice in order to actually graph this using slope-intercept form, you would have to extend the line further. So if you're graphing this on your own paper, graph the entire line, figure out where the line is cut off, and then just erase the portion you don't need. So we only want to keep the portion up to -1, but not including that point at -1. So that's the first piece of our graph. The second piece comes from f of x is equal to x squared. This specifically applies for x values between -1 and 2, including -1, but not including 2. So notice something different has happened here. We aren't continuing on to infinity. So specifically, we're stopping when we get to x equals 2. We don't have any rules in our function that tell us what happens at 2 or anything above 2. So we just assume the graph stops there. We don't have any additional information, so that's where our graph has to stop. So this is the quadratic parent function. Remember, it's centered at the origin. It looks like a U. But we're only keeping the portion from -1 to 2 on the x-axis. So we're only keeping the portion of this graph where the x values go from -1 on the left to 2 on the right, including the point at -1, but not including the point at x equals 2. So we only have a little piece here. This is a finite piece of graph, whereas the first piece continues to the left forever and ever. So we combine these two graphs together, and this gives our piecewise-defined graph. Notice that point at -1. There is a clear break in the graph, whereas our previous one, the two pieces happen to join together at the same point. That doesn't always happen. In this case, we have a clear jump in the graph. So on the first piece of graph, we have a hole. We jump to the second piece of graph and it actually fills in our point there. So at x equals -1, we have one point that's defined, we have one point that's an open circle. So if we were to evaluate this particular function for x equals -1, we'd specifically use the second rule as opposed to the first rule. So far in this section, we've talked about different ways we can classify equations based on what their graphs look like. So first we talked about symmetry for a generic equation as well as for a function. And then we talked about piecewise-defined functions, which are specific functions whose graphs are disjointed. Each portion of the graph is defined by a different function rule. Finally, we're going to talk about classifying inside of a function. So inside of a function, we can determine where a function is increasing, decreasing, and constant. And this just tells us what way the function's graph is sloped, going from left to right. So we have three types of behavior, and every function can exhibit all of them in different portions of its domain. So a function is increasing on an interval in its domain, in other words, on a portion of x values, if for our values going from left to right, in other words, smaller x to larger x looking left to right, the function values are also less than one another going left to right. So in other words, increasing just means sloped upward. So as our function values, or excuse me, as our x values get bigger, our function values are also getting bigger. So we're sloped upward. Another possibility is that we're decreasing on an interval. So as we're going left to right from smaller x values to larger x values, now our outputs are getting smaller. So going from left to right, our output is going from a higher value to a lower value. This looks like a slope downward. And then finally, we could possibly have a situation where we're constant on an interval in the domain. So as our x's are going left to right, our function values are not changing. This looks like a flat horizontal line, in other words, a slope of 0. So one thing to keep in mind is we cannot determine what happens at corners. In other words, where we go from being sloped upward to sloped downward or to a flat line, any spot where we change behavior. So when we're defining the intervals where specific types of behavior are happening, we don't include these corners in the intervals because we can't officially say, well, which side is that one on? Is it on both? Is it on neither? This means that when we write our intervals, we're going to write them with parentheses. So we're not actually going to include those corners where things change because we can't officially say what's happening at a corner. It could go either way. So essentially what we're doing is we're breaking apart the domain into pieces. Each of these individual pieces is defined based on how the graph is sloped over those particular x values. So technically increasing, decreasing, and constant areas can be defined in terms of an equation. However, we need a little bit more information to determine where our graph is increasing, decreasing, and constant strictly from an equation. So for our purposes, we're just going to look at a graph and we're going to determine what's happening specifically from a graph as opposed to something in function notation. So let's look at an example of a graph where we determine the intervals over which the function is increasing, decreasing, and constant. So keep in mind we're only talking about the domain, we're talking about the x values. So we're taking the range of x values and we're breaking them down into individual pieces based on whatever behavior the function is exhibiting over those particular pieces. So here's our graph. We definitely got some sloped areas that change direction. So once we change from one to another, that's going to be the breaks in the intervals. So keep in mind, we don't specifically care about where the function ends up. All we care about is the specific behavior and which x values that behavior is occurring over. So I like to just take the x-axis and break it down into pieces. The x-axis always represents the domain, so we're breaking the x-axis, we're breaking the domain down into pieces based on what's happening in the actual graph over those particular pieces. So starting from negative infinity, looks like stopping at -2, we have an upward slope. So even though the arrow is pointing downward to the left, don't let that fool you. As we look from left to right, like we're reading, it's an upward slope going from left to right. So everything from negative infinity to -2 on the x-axis is increasing. It's an upward slope. Once we get to -2, we flatline. So -2 to 0, we now have a constant interval. So it's a flat horizontal line until we get to 0. From 0 to 2, we go from constant behavior to decreasing behavior. So now we're sloped downward left to right. And finally, once we get to x equals 2 and then continuing to infinity, we're sloped upward for the rest of the domain. So this is an increasing portion. So we want to take each of these intervals and write them in interval notation, combining them using union if we have any common intervals for different types of behavior. So our increasing areas are from negative infinity to negative 2. That's one increasing portion. And then from 2 to infinity. So notice we have two intervals here. We combine them with the union to show that both are included as increasing intervals. Again, keep in mind we didn't say anything about what the actual y values were, where we started or where we ended. All we care about is the fact that over these particular x values, we are sloped upward, we are increasing, our y values are getting bigger. For the decreasing range, that's from 0 to 2, and then our constant range is from negative 2 to 0. So notice if you took all of these intervals and stuck them together in order, you would have the whole domain except for those corners. The corners, again, we don't really know what's happening at corners, so we don't include the corners. But if you were to stick all these intervals together, you would have the entire domain, the entire x-axis, from negative infinity to infinity. So breaking a graph down into increasing, decreasing, and constant intervals is just another way of classifying the graph, classifying some of the behavior we see that may give us some more information later about what the actual function is doing. Let's summarize what we've learned in this section. So equations and graphs can be described in terms of their symmetry. That's one type of classification. We have three possible symmetries: y-axis symmetry, x-axis symmetry, and origin symmetry. And we have three different tests, one to determine whether or not each of these applies. So to determine whether or not a graph is going to have y-axis symmetry from its equation, we plug in a negative x in place of x, and if we can eliminate the negative from the problem, then we have y-axis symmetry. To check for x-axis symmetry, we plug in a negative y instead of a negative x, and if we can eliminate that y, get it back to where it started, then we have x-axis symmetry. And finally, origin symmetry, if we plug in a negative x and a negative y and both can be eliminated, we can return to the original equation in its original form, then we know we have origin symmetry. Specifically for functions, we talk about evenness and oddness. So these are the conjugates of the symmetry check for generic equations in function form. So an even function, if we plug in a negative x, all the negatives go away. We return to the original function without any changes made. In other words, all the signs from the original function are the same for the resulting function that we end up with. That's one possibility. A function can be even. If we plug in our negative x and it flips all the signs, so it makes the original function negative, all the signs are flipped, then we have an odd function. We can also have a function that's neither even nor odd. So an even function is going to have y-axis symmetry, an odd function is going to have origin symmetry, and a function that's neither even nor odd is not going to have any specific symmetry. We can also break a function down into regions where the domain is increasing, decreasing, and constant. So looking from left to right, we're just determining, is the graph sloped upward, is it sloped downward, or is it a flat horizontal line? So we're breaking the function down into pieces based on what's happening in the graph. And then we also talked about special graphs that are defined by functions who have separate individual rules for different pieces of the domain. So we call these piecewise-defined functions. They're defined by multiple rules, each applying to a different interval of the function's domain.